But that doesn't make sense. Why would we? Oh, what do we have a Monday off? We have a Monday off, maybe? Labor Day. We have Friday off. And we have tax, so that means we should be more. We should be 1 month 3. What did I finish by saying last time? Where's the yeah. Oh yeah. So I went to go back. He said you can't go on
Yeah, he's done that. Okay, so you're wondering about
You gonna watch upstairs?
So he uses some ideas that
Okay, so having talked about handle bodies last time, we're ready to talk about Meier splittings. That's 3 minutes. Part 2. All right. So from this point on, I think we'll let Y be a closed, connected, orientable, maybe sometimes oriented 3 manifold. Okay. So genus G Hager splitting. Of Y is a decomposition. Y equals H1 union sigma H2 such that we have 2 things that are true. So first we want these pieces to be handle bodies. So HI is a genus G handle body. This is for I equals 1, 2. And then I guess that's enough, except maybe we'll just to be clear, we'll say that the sigma is which should be identified through the HI. And so of course it is a closed genus G surface. And sigma is a Hagar surface for Y, and G is the genus of the Hagar split. All right. So we have a Hagar splitting, we have a Hagar surface. So a Hagar surface is a closed surface in a 3 manifold that splits into 2 handle bodies. Splitting, and G is the genus of the splitting. Okay. And I guess the last thing to say is 2 things to say. First is that we consider sigma up to ambient isotopy. What do I mean by this? I guess maybe I should say we consider the splitting up to ambient isotopy of sigma. So 2 Hagar splittings are isotopic if there's an isotopy taking sigma onto itself. Now, if Y is oriented, then by convention we say that Y is the first handle body union the mirror of the second handle body, and that sigma is oriented as the boundary of the first handle body. Okay, so I found this interesting remark in the introduction to there's a book of Charlemagne Schulten's on general Haggard splittings, and they talk about where they give a little note about the history of a Haggard splitting. So Haggard splittings were first conceived by Paul Haggard. I'm going to speak Danish. Paul Haggard, all the way back in his 1898 thesis. So that's pretty cool. And he conceived of them as a way to criticize the work, to critique the work of Poincaré. Who had come up with some notion of homology and some notion of duality. And so I guess the point is that Poincaré's, what did I write here? This doesn't look quite right. Is that right? I think it's I. Yeah, thank you. Yeah, much better. Apparently, Poincaré's original work on this duality of homology from manifolds was wrong because he wasn't, he lacked the notion of torsion in homology. So he was talking about things like Betti numbers and trying to formulate homology and duality that way, and which ended up working out. But because of the sort of oversight of torsion, I guess Paul Haggard was able to give these examples of three manifolds where homology wasn't quite what was expected. Oh, that was kind of cool. And so then Poincaré fixed it. Apparently, this forced Poincaré back into topology. Apparently, he had done this work and then migrated off into other areas, and then he came back. And I guess this probably would have been, I don't know. It seems like this would have been pre-Poincaré conjecture. Which I think he also kind of erroneously conjectured that there would be that if a three manifold had the homology of the three sphere, then it would be the three sphere, homomorphic to the three sphere. But I think he realized that that was not right. I guess maybe that now that I've gone through my understanding of the story, it seems like that probably would have predated the notion of homology. Anyway, so the Poincaré homology sphere came out of that. Okay. Great. Okay, so then the main theorem that is of interest. It's interesting that this theorem is so much farther removed from the advent of this. I also looked at maybe it was a translation of Haggard's paper. I don't think I had any pictures in it, which is a little disappointing. I guess maybe people did topology a little bit differently back then. Okay, so the theorem, which is attributed to Meier and then Bing, both of these people proved this in Annals papers, which is, well, the statement that we'll be interested in is that every closed, connected, orientable three manifold a genus G splitting, genus G Haggard splitting, for some non-negative value of G. So what they actually proved is that these objects admit triangulations. And from a triangulation, you can get a Haggard splitting. And so maybe I'll just try to give an idea of how that works. So you have a triangulation of your three manifold. That means it's cut up into these tetrahedra. Let's see, can we do another one? Maybe we don't want that. And so then this is, it's a cellular decomposition of a special type. And so what you do is you take a regular neighborhood of the one skeleton, the 0 cells of the 1 cells, like this. And by definition, that is a handle body. And so now the question is, what is the remaining bit? Well, the remaining bit is 2 cells and 3 cells, but there's a dual triangulation in which we have, a vertex and an edge for each. We have a vertex for each 4 cell and an edge for each 3 cell. And so we actually see the skeleton is a neighborhood of the 3 skeleton, 3 and 4 cells, which is actually another 1 skeleton. Okay, so we get a complementary handle body inside there. And if you do this properly, maybe take a second barycentric subdivision, these 2 handle bodies meet along the closed surface. So from a triangulation, we get a Haggard splitting, but it took some serious work in the 1950s to prove the existence of triangulations for 3 dimensions. Okay. Any questions? Oh yeah, maybe I should mention is that I found some really nice lecture notes by Jesse Johnson. I think they're called lecture notes on Haggard splittings. So if you want a reference that goes into a lot more detail, sort of thorough grounds-up approach, I highly recommend taking a look at that. I'll be picking and pulling from this and doing some things, but not in as much detail as he does that. Okay. So our next definition is that of a genus G Haggard diagram. So a genus G Haggard diagram is a triple sigma alpha beta, such that first off, sigma is a closed genus G surface, and second, I guess alpha, which we think of as G, the collection of G curves, is a cut system. Cut system for sigma. Remember, that means that if we surge your sigma along sigma, if we surge your sigma along alpha, we're left with a 2 sphere. And same thing for beta. So it's a surface together with 2 cut systems for the surface. Each one of these cut systems determines a handle body defined by those curves. And so this Haggard diagram, we start with something like this, a surface. And we have some alpha curves. And the alpha curves tell us how to attach disks that surge the surface down to a sphere and can be capped off to give a handle body H alpha, which in this picture would be on the inside. And then likewise, the blue beta curves, so beta 1 and beta 2, also tell us how to attach disks so that the surface is surged to a sphere and can be capped off to give another handle body. So we get a decomposition of Y into H alpha union along sigma H beta. So genus G Haggard diagram determines a genus G Haggard splitting of some 3 manifold. This theorem is that every 3 manifold, every closed, connected, organizable 3 manifold can be described by a genus G Haggard diagram. So Haggard diagrams give us a nice way to describe and study 3 manifolds. And so what is the proof of this corollary? Well, once we have our Haggard splitting, we just choose cut systems of disks for each of the handle bodies, and we draw their boundary curves on the boundary surface.
Do you still want to think of what we're actually seeing there with the HK bar?
Yeah, I do want to keep track of the orientation, that's right. I think for the most part, I will keep track of it. I won't really be that interested in distinguishing different orientations of the same manifold, I don't think. Okay. Okay, so let's think about some examples. Okay, so the first example is, well, because we associate a natural number or 0 to a Haggard splitting, we can think about just sort of studying these things in numerical order. So the first thing to think about is G equals 0. And what this means is that we've decomposed our 3 manifold as the union of 2 3 balls along a 2 sphere. And so this implies that Y is actually the 3 sphere. So there is a unique genus 0 Haggard splitting. Okay. So then the next thing we can start thinking about is genus 1. And so there's a couple of nice examples that show up here that will be important for us. So to think about a genus 1 Haggard splitting, I really just want to think about take a genus 1 surface and draw a red curve and a blue curve on it. And so maybe the first way I try to do this is to draw these curves so that they intersect in a single point. So this would be alpha, this would be beta. And this is a particularly nice surface that we've already seen is this gives y equal h alpha union h beta. But one way we could think of this is actually the red handle body is a solid torus, so we can write it as, let's say, D2 cross S1. And then we're gluing along torus a copy of S1 cross S1. And the second handle body, because these curves intersect at a point, is just a copy of S1 cross D2. So they're both solid tori, but the factors S1 and D2 have been reversed. Okay, and so we've actually seen this before because this first factor, I think, let's think of this as H alpha, we can think of this as a neighborhood of the unknot in S3. So if I bring my unknot into play here, the unknot is sort of living inside that alpha handle body, and the alpha solid torus can be thought of as a regular neighborhood of that. Then this piece here is just the exterior of the, maybe this is the closure of a regular neighborhood. This piece is just the exterior of the line. Okay, because when we remove a regular neighborhood of it, we're left up with a solid torus. And so we see that again, this implies that Y is S3. I think another nice way to think of this, so if sigma is the genus 1 Haggard surface for S3, so it's sitting inside S3, then one way to think of this is if we take S3 and we remove a neighborhood of a hop plane, then what we're left over with is just this surface cross I. So let's think about that. So what I'm picturing here is, I should draw it. We have one component of the hop length which we thicken. And then we have another component of the hop length, which we thicken. And so as an exercise, you can check that what's left over is a torus cross I. In particular, the fundamental group of S3 minus the hop length is the group of the torus. Okay, that's just a little aside. Okay, so continuing, maybe this was part 2A, and this is part 2B. So the other natural way, the next most natural way to draw our curves on here is to, again, pick our alpha curve to be something. And then we could pick our beta curve to be the same thing. And so since we consider these things up to isotopy, it's natural to you know, we could either, it's a little awkward to draw beta as the exact same curve as alpha. But really, really that's what's happening here, just draw it slightly push off. And so what happens here is we get a decomposition similar to this, right? We have that, in this case, Y is, again, we can think of the alpha handle body as D2 cross S1. So maybe something I'd like to emphasize here is that when we attach this alpha disk to the solid torus, or to the torus, what we really get is a circle's worth of disks filling in the torus. Right? Some of these come from the 2 handle, because the 2 handle is a disk cross I. But then the remainder is another 3 ball, you know, the 0 cell or the 3 cell. And that also can be thought of as a disk cross I. So when you attach a curve to a solid, this will come up in a couple of places. We're talking about 3 manifolds, but when you attach a solid torus to a torus, you're really attaching a circle's worth of disks. So all of the curves that are parallel to alpha found in the alpha handle body. So that's how we sort of see this as D2 cross S1. But then what we're seeing is that in this case, we're also attaching, maybe this comes to the outside, we're also attaching a circle's worth of disks to beta, and it's all the same curves that we're attaching them along. So again, we're unioning along a torus, but this time, second solid torus has the same parameterization as before. And this union is this is the sort of canonical decomposition of S2 cross S1, because we're just gluing a disk cross S1 to a disk cross S1 so that the boundaries of the disks agree. And so here we have S1 cross S2, which, so you can apparently think of as something like this. And you want to think of this as a circle's worth of spheres. Well, you get a circle's worth of southern hemispheres, and you get a circle's worth of northern hemispheres. And the circle's worth of each hemisphere is a solid torus, and the circle's worth of equators is the Hilbert surface. So sigma is S1 worth of equators of S2. That's a quote. Okay. Any questions?
So we didn't talk about any gluing map or anything like that. We said that actually picking the CAD systems will determine the two hand bodies. Is it correct to think that in another way, if I pick the CAD system, is it like that the CAD systems will determine my gluing map, or it's not correct to think about it like that?
Yeah, so the way I've tried to build these things so far is to start with the fixed surface and attach handles in each direction. And those handle attachments are determined by these attaching circles. You know, an alternative way to think about this would be to take some solid torus, some abstract solid torus, and some other abstract solid torus, and to glue this one to this one by some diffeomorphism of the bound, you know, maybe T1 to T2, where this is I guess H beta, or maybe it was H2, and the boundary of H2 is T2, and this is H1, and the boundary of H1 is T1, and we have some homeomorphism of the surface when they catch it. In that case, we end up being interested in the same thing. What we're interested in is where this curve goes. And so this curve, right. So the reason we're only interested in where that curve goes is, I guess a priori, since this is a diffeomorphism of the torus, we're actually interested in where, say, this curve lambda and this curve mu go in this picture. As a diffeomorphism of torus, we need to keep track of where both of those curves go. But because this torus is bounding a solid torus, the image will be determined by where mu goes, because we can always pre-compose with Dane twists around mu to affect where lambda would go, right? So for example, in this example, I guess we're taking mu onto this guy, right? And now there's a question of where lambda could go. Well, because it's a homeomorphism, lambda has to hit this in a single point. And so what it could do is it could kind of wrap. It could wrap in that direction. But that's just like pre-composing here with Dane twists along mu that wrap lambda. Another way to think of that is that the diffeomorphism of the torus that sends lambda onto this, and the diffeomorphism of the torus that sends lambda on the twisted one, they extend. Sorry, what do I want to say? I guess the difference between these diffeomorphisms, which is this twisting, extends over the solid torus because it's twisting along the curve mu, which bounds the disk. But you're right that in general, one way to think about three manifolds is to take two handle bodies and glue them together. But all that ends up mattering is where the cut system of curves gets mapped to. So you could think of this as being like, you know, you could think of this as H union H via phi, where phi is like, you know, phi sen, it's like this, is it this matrix or something? And I guess some sort of any matrix of this form or something, right? Where it's sending the red curve to the blue curve, swapping the factors, something like that.
Like having two hand bodies and including the CAD systems along the corresponding curves.
Exactly, yeah, exactly, that's right. This one you'd be gluing by the identity, And then, you know, actually, normally length spaces are introduced in this way. You think, okay, well, what are all the automorphisms of the torus? Well, I guess it's, what is it, SL2Z? Or is it SL2Z? Okay, SL2Z. And then which ones are going to extend over the solid torus? And then this gives you sort of family of what I call length spaces. So far, I've given you two examples of genus 1 Hagar splitting that are just given by the most obvious choice of where to send the second curve. So the final family, again, we might as well sort of start with our favorite curve here. But then we can attach our second handle along sort of any curve on here. And so in particular, we can attach it along a PQ curve. If you think back to when we defined torus knots on the second day of class. I always want to say the first day of class, but it was actually the second day of class where all of the important stuff happened. Right. So in this case, we let beta be an NM curve. And if you remember what an M curve means, it essentially means that it winds around in this direction M times, and it winds around in the winds around parallel to alpha M times, and runs transverse to alpha, or N times, and runs transverse to alpha M times. That's very difficult to say. But this, I should say that this is a 5-2 curve. That makes it more clear. A 5-2 curve. In particular, it's in the homology class that is, 5 times this longitude and 2 times the meridian. And this gives rise, so this is beta, so this gives rise to length space, what's called a length space, L, M, N. So in this particular example, we would get L5-2. And maybe I'll just say sometimes S3 and S1 cross S2 are considered as length spaces. And just by considering the entirety of curves or pairs of curves on the torus, this is a complete list of manifolds that admit genus 1 Hagar splittings. And maybe you call the class of such thing length spaces. I guess there are times when people don't want to consider S3 and S1 cross S2 length spaces. Okay. Oh, I have one more example I want to give. Okay, so the last example is the 3 torus, which is the product of 3 copies of S1, which we can also think of as start with R3 and mod out by the integer length. So what does that look like? Well, I guess we take a bunch of copies of the y-axis, a bunch of copies of the x-axis, a bunch of copies now in show of the z-axis. Oh man, so many things. Okay, hold on. Let me just draw it like this. Change of approach. So inside R3 we have lattice central points. Yeah.
Did you mean to do that? It says in white LMN, and then you have in white blue.
Yeah.
You didn't.
I think I meant to do that.
Just for clarity.
No, that's a good point. Yeah. So,
Right. The issue to the PQ length space is the group. The beta is QP. I think that's right.
yeah, the question is, what do you call a PQ curve or a QP curve, right? And the problem that I've had with this is that there are two aspects of knot theory where you're really interested in these curves. One is if you're doing Dane surgery, then you want to fill along a PQ curve. And the other is if you want to do cabling, where you take like a solid, we talked about on day 2, and you, let's see, I think that's right. So this would be, let's see. What do I mean by that? Well, I don't know. Maybe it's just a convention. Okay. But there's like a minor issue that arises here. So I mean, this is what you would see, because this would be if you did surgery on this. What am I trying to say? That's right. So this. Okay, I don't want to.
I think you have it right.
Yeah. Well, I mean, I have something that's one point, but now I'm getting confused thinking about these surgery.
So for example, pi 1 of this space is z mod 5.
Pi 1 of this space is z mod 5. That's definitely true, right? And so, oh no, but this is wrong. No, the whole point is that what I've written on the board is inconsistent, right? Because here I call M2 and here I call M5. Yeah. Okay, so there's a problem. So that's, okay, so this is a 2-5 curve. Going this to be a 2-5 curve. Well, now I don't remember. What did I do in my notes? Yeah, NM curve, LMN. Now I got up to. Oh gosh, the whole universe is gonna fall apart. All right. Okay. Well, I'll tell you what. We're gonna talk about Dane surgery soon, and so when we get to Dane surgery, I'll look extra carefully, more carefully than I thought I would, at what I said in lecture 2. The problem is I'm stuck by whatever I said in lecture 2. So, okay, but now I'm curious. Okay, well. Oh, I mean, there's an extra, okay, maybe I'll just say this. There's an extra complicating factor, which is that boundary of H alpha may do 5 curve. But if you don't that boundary of H beta, it's a 5-2 curve. That's the problem. And so, for example, if we wanted to think of this as surgery on the unknot, then we think of the unknot complement as being the outside, so we view it as 5/2 surgery on that. So that's what I think. That's the point. That's a point. Okay. No, but actually, thank you for bringing it up because there was an error. Okay. So I tried to make this match my notation for rational links. And yeah. So okay, exercise. Exercise is compare with day 2. So day 2, I talked about torus links and rational links. And torus links involve these curves, and rational links involve the letters M and N. And hopefully everything's consistent. It would be good if it was. Okay. All right, so what is the 3 torus? Well, it's where you take all points in R3 and you mod out by translation by integers in all 3 directions. So the fundamental domain for this action is going to be a unit cube. So we can draw where the top is identified with the bottom because the top gets identified. Right is identified with left, and front is identified with back. So this is what the 3 torus looks like. Solid, it's filled in. So then what does the tangent surface look like? Well, it's like this. something like that. You have this, so what I've sort of drawn here is an orange handle line. So I get alpha curves that bound disks to the inside that look like that. And if you think about all the arms of this 6-armed beast, is that you'll get a genus 3 surface. Sigma is a genus 3 surface. And so that I have the, and I'm thinking of it as sort of filled in the obvious way with the red handle body, so we see H alpha. And then what you can check is that the exterior of this handle body is also a handle body inside the 3 course. And so maybe I'll draw at least one of the blue curves. So it sort of wraps around here. So you should think of this as bounding a disk kind of like this corner disk. Yeah, maybe I'll draw this out. Let's draw that. This corner disk, but then it comes in over here. Comes out like that. So there's another corner disk here. And since it's this edge, it also comes in over here. So there's another corner disk here. And in the back, there's another corner disk. So this would be beta 1. And the disk bounded by beta 1. And so there's 3 of these. One basically in each plane, coordinate plane of 3 space. And so this gives a genus 3. So T3 has a genus 3 Hayes plane. And just in case we don't return to this, it's actually minimal. You can't do smaller than that. And it's also unique up to isotopy. That's a result of Johnson. I don't know what the year it was. Pretty recent, actually. I think it was like 2011. Okay, great. So those are some baby examples of Hagar splittings. And then, of course, I mean, maybe example 5 is just something like this, right? Maybe example 5 is just draw a crazy surface, or maybe a not so crazy surface, maybe not so crazy alpha curves, but then you just draw really crazy beta curves, which is pretty hard to do when you actually start doing it. Something like this. And okay, now I'm in trouble. Gotta go in here. Gotta go right here. But you have these baby examples, and then you have all 3 methods. And it's not such a problem, it's just drawing curves on a surface. Okay. This is why. Okay. So since we have this notion of a Hagar diagram that allows us to input 3 manifolds, we need to write down what the sort of overdetermined. So two Hagar diagrams are, let's say, slide equivalent. Oh, these things names are sigma alpha beta and sigma alpha prime beta prime. Oh, it's I don't want to say slide equivalent. So there's a notion of equivalent alpha if the following is true. If sigma prime alpha prime beta, I'm not going to define slide equivalent to sigma prime alpha double prime beta double prime. there's a diffeomorphism of triples between sigma prime alpha. What do I mean by two diagrams being slide equivalent, right? That just means I do some slides of the alpha curves over themselves, and I do some slides of the beta curves over themselves. Equivalence of cut systems of curves, so it's just two copies of that. So for two diagrams become diffeomorphic. So let's look at an example of this. So suppose, let's see. So suppose somebody hands you this diagram and asks you to tell them something about it. So this is a nice Hagar diagram with two beta curves and two alpha curves. Different names. Beta 1, beta 2, and alpha 1, alpha 2. And this is going to be our, oh, except I want these all to be prime. This is going to be the prime guy. Because what I'm going to do is I'm going to slide alpha 2 prime over alpha 1 prime. There's sort of an obvious handle slide there that one might want to do. If I slide this over, it will come unhooked. And I'll get this. I'll call the new thing alpha 2 double prime. I'll call the new copy of alpha 1 prime betas to double prime status as well. And of course, the sigma, the surface is still sigma. This looks pretty nice because the curves intersect Kronecker delta. But we'd like to sort of compare it to what might be considered our favorite genus 2 Hagar diagram, where this is beta 1, this is beta 2, this is alpha 1, this is alpha 2, this is the surface sigma. And of course, there's a diffeomorphism. Taking this surface with these curves on it to this surface with these curves on it. Okay, it's the diffeomorphism that sends this curve to this curve and this curve to this curve. So what I want to sort of emphasize with this slide diffeomorphic is that there's sort of two ways of, there's kind of two things I want to emphasize. Well, one is that you can just slide the curves around. So for example, here I'm not imagining the surface changing, right? I'm imagining doing something on a surface. I just drew two copies of it. But over here, I have a different surface. It's a different diagram. These curves are living on a different surface. So it doesn't even make sense to talk about sliding these curves to this one. But it does make sense to compare them by diffeomorphism. Alternatively, if I were thinking of these as lying all on the same surface, then they'd actually be defining different handle bodies because this curve bounds in this alpha handle body, but not in this one. And so I would need a self-diffeomorphism then of the surface that takes the curves. So the point is that the right way to compare diagrams up to slide it. Okay. And so the corollary to the fact that we had from last class that about when two cut systems determine the same handle body is that two Hagar diagrams determine diffeomorphic Hagar splittings. If and only if. So I guess this isn't something I really talked about before because I said we consider Hagar splittings up to isotopy of the sort of Hagar surface. We can also, if we're handed two different manifolds with Hagar splittings, we can ask if there's a diffeomorphism of the manifolds that takes the pieces of the Hagar splitting onto the pieces of the Hagar surface. In particular, takes the Hagar surface onto the Hagar surface.
Do you want the same genus?
Well, Yeah, I mean, yeah, that's a good question. It's implied because if they're slide diffeomorphic, then in particular the surfaces are diffeomorphic. And if they determine diffeomorphic Hagar splittings, then again the surface is implied here. So in particular, two Hagar splittings or Hagar diagrams of different genus are not diffeomorphic or slide diffeomorphic.
Do you require this diffeomorphism between surfaces to be orientation preserving?
Well, I think that's user's choice. Yeah, you can.
So you could strengthen this corollary by saying.
Oh, I see.
orientation preserving.
Oh, that's a good point. I guess,
I mean, that's only up to plus or minus.
yeah. I guess maybe I should, well, okay. When I say diffeomorphism of triples, I mean that the alpha handle bodies go alpha handle implying orientation preserved. Yeah, good question. Okay, I think that's it for today. I'll see some of you on Wednesday. And we have 2 good talks this afternoon. So let's end it there. Who knows how to do this thing? Maybe Dave's looking inside. All right. I think I pushed end stream.
Next year.
End stream.